coordinates in. So I'm going to type in coordinate 1, 2, 3, and 4, 5, 6. I'm going to zoom out just a bit since that second point is not in view. So in Desmos 3D specifically, something we can do is we can type vector, and you can draw a vector starting at 1, 2, 3, and ending at 4, 5, 6. And Desmos will sketch or draw a ray that starts at the point in red and ends at the point in blue. Unfortunately, for whatever reason, this doesn't work in Desmos 2D. It's only a 3D thing.
Oh, okay. Nice.
So if I want this in standard position, we said that means to pick the vector up and drag it all the way such that the starting point is at the origin. We can write it in component form by doing final minus initial. So I can have the vector 4 minus 1 is 3, 5 minus 2 is 3, 6 minus 3 is 3. But, of course, that is a coordinate only. So the way that we can get that to be a vector is say vector starting at 0, 0, 0 and ending at 3, 3. Now you can see exactly what's happening here. I have two vectors that are parallel or scalar multiples. But the one in blue is just in our quote-unquote standard form where it starts at the origin. But a lot of this seems kind of annoying to type all that in. So my recommendation to you is you can call this point A, say A equals. You can call this B, B equals. Now you can just draw the vector starting at whatever we're calling A and ending at whatever we're calling B. Very similarly, I would just call the point O 0, 0, 0, like the origin. So now when you're drawing all your vectors, you can say, draw the vector from the origin to A, or something like that. Or you can say from the origin to A plus B. In fact, Desmos does no vector addition. All right, another fun thing you can do. Say I have the point -2, 4, 5, and let's see, 2, 3, -1. So while these are coordinates, I want to think of these as vectors. So again, I'm going to call O the origin, 0, 0, 0. And I want V to be the vector from the origin to what I'm going to call point A. And I want M to be the vector from the origin to what I'm going to call point B. Desmos does know dot products. So if you write V dot M, you start looking at the picture and we're like, well, hang on, it's not drawing anything. Oh, okay, that's right. The dot product we said was a scalar. It just gives a number back. So it's almost like it's doing a calculation over here, and it says V dot M is equal to 3.
Question.
Yeah.
I was looking it up last night. Is there any way to find the angle between those two vectors?
Yes. So the angle between the two vectors was,
The dot product over.
it was the
adaptive
inverse
value
cosine.
of-
Yep.
Right, inverse cosine. Value of vector to UV.
That was how to find the angle between the two vectors.
Mhm.
Yes.
Repeat the dot again.
Shit. So it's like the multiplication symbol.
Oh, shit, that. Okay.
But I mean, I know what it is, but I mean, is there any way to do that in Desmos?
So you could do arc cosine. Let's play around with this for a second. Let's see if I can type in something to get the magnitude. Ah, very cool. If you type the absolute value,
Mhm.
it's going to calculate the magnitude. And let's double, triple check that that's doing that correctly. If I go all the way up to vector A, or I'm sorry, what we call vector B, to point A, that should be the square root of -2 squared plus 4 squared plus 5 squared. And drum roll, there it is.
Okay.
So to get the angle between the two vectors, we can do arc cosine of V dot M divided by the magnitude of V times the magnitude of M. But we probably want this in degrees.
Oh, look at here, look at it.
So yes, you can do it in this place.
Okay. Okay. Yeah, I was trying, I couldn't figure out how to do it last night.
Alright, so this is always just going to be a practice with experimentation, kind of seeing this for the first time. We're a little thrown off, we're like, okay, hang on, how do I get it to draw the vectors again? We're going to have an entire class where we're just on Desmos playing around with different vectors in 3D space. But we are interested in kind of our last vector operation, which is called the cross product. Alright, so we've got vectors, we saw we can add them, we saw we can subtract them, you can scale them, you can find the dot product. So now one of our last vector operations is the quote-unquote cross product. So our notation for that is V cross U. So important here, this gives a vector. So don't forget, like we saw with the dot product, it gives you a scalar or a number. So now we're going to do some sort of operation that actually gives you another vector. And it's going to be a vector that is perpendicular to both V and U. So I'm going to put my two markers out. Any two vectors that you give me with any kind of angle, any way that you want to put the two vectors, this cross product is going to give you a third vector that is perpendicular to the two of them. Now you might be saying, well, hang on. Well, what if I wanted this vector, which was also perpendicular? So this is where we get into that quote-unquote right-hand rule. So if you want to know the direction that your cross product is going to give you, you take your right hand, you put your index finger in the direction of the first vector, your middle finger in the direction of the second vector, and that gives you the cross product. That's going to show you the direction that that third vector is going to be. Now you could switch it. If you want to do first vector, second vector, now my thumb points in the opposite direction. So something important to know, V cross U is not commutative. Meaning if you change the order here, you do not get the same thing. That was not true for our dot product. When we did the dot product, it was like, oh, well yeah, it kind of makes sense that you can change the order. That does not happen here with V cross U. It gives you a different vector. All right, Claire, give me your favorite 3D vector.
Me? Any of them?
Your favorite specifically.
My favorite. I don't know if I have favorites. So I need to choose from. 3, 9, -2.
What's your favorite 3D vector?
1, 2, 3.
I think that's my favorite too. 1, 2, 3. Solid. We're going to show kind of the operation of how to get this cross product, and then I'm going to leave it to you guys in Desmos to practice graphing it, make sure we can see it correctly. All right, so if we want the cross product, we are going to put the two vectors in a matrix with 3 rows, I hat, j hat, and k hat. Vector v written second, and vector u written third. Super important, the order of the rows do matter. So the first row is always going to be I, J, K. The second row is always going to be the first vector. If we're doing v cross u, we want to make sure that we put v first. Again, changing the order does give us a different answer. And now we're going to put absolute value bars when we put those absolute value bars on that matrix, it's just saying, take the determinant of. So the determinant is a skill from linear algebra. We're going to kind of just run through it very quickly, appreciating it and the theory behind it. I'll be honest, it's not really something we're interested in for this class. We just need to know how to do it for our calculus tools. So this process is what we're calling, quote unquote, expansion by minors. You're going to grab I hat, the top left entry. You're going to cover the first column and the first row like this, and you're left with a 2x2 matrix. So you're going to write that down. It still has those absolute value bars showing we're still about to take the determinant of that matrix. Then it's going to be minus j hat. The middle one's always going to be negative. And now, same idea. Cover the column and cover the row that has j hat in it. And now you're left with a 2x2 matrix. So again, for j, I'm covering up the column that has j, covering up the row that has j, and I'm left with 4 entries. I'll give you guys a 2-second head start. And I have plus k. Make sure we can practice seeing this. Now you're going to cover the row and the column that have k.
Why is it plus K?
So it's always just going to be the middle
Plus
one.
minus plus.
Oh, okay.
It was plus minus plus and minus plus minus and plus minus plus. You're doing
So
all
covering up the
those.
row and the column with K, I'm left with 3, 9, 1, 2. We'll pause there for 2 seconds. Alright, taking a big step back. I want V cross U. All that means is you're finding the determinant of this matrix. So this is just this idea of you cover it up, grab a 2 by 2, so I've got I hat times the determinant of this matrix. Minus, it's always going to be minus for the middle one, J hat times the determinant of that matrix, plus K hat times the determinant of that matrix. So again, those absolute value bars are saying take the determinant of. If you want to do it for a 3 by 3, we have to do this expansion by minors. But now that we want a 2 by 2, this is where you do 9 times 3 minus negative 2 times 2. So once we've gotten it to a 2 by 2, you do 9 times 3 minus, and then you do a loop around. So it's 9 times 3 minus negative 2 times 2. So minus J I've got 3 times 3 minus negative 2 times 4. Give you guys a 30-second head start to practice finding the determinant for that last piece. The last one should be 3 times 2 minus 9 times 1. Please ask questions on that. So now we just clean it up. So I'm just going to take 2 seconds.
31.
Just do all my algebra, or
31.
arithmetic rather.
31. Negative 3.
So again, all I'm doing here is, these are just numbers. This is something you could honestly just plug in a calculator. You guys are gonna get so good at this that you don't have to show me this step even. Once you get here, you can go, okay, 9 times 3 minus negative 2, okay, got it, boom, and then just run to it. So I remember that I, J, K is just another way of writing a vector, and I remember, okay, that's right. But at the end of this cross product, I should get a vector back that is perpendicular to both of them. So I'm just going to come back over here. We wanted V cross U, and I got the vector 31, negative 11, -3. I do want to practice graphing this in Desmos, but just to make sure we're solid on the cross product, we're going to do one more of these and then spend some time visualizing what exactly our answers are looking like. Honestly, the only way that this is just going to become fluent is just drill and kill. We just have to do a couple of these over and over. All right, Chloe, what's your favorite 3 vector?
3, 2, 7.
And then Tanner?
2, 4, 6.
All right, so now we want B cross A. Just be careful, the order does matter. So we want to make sure that when we set it up, that our second entry, our second row is the B vector. Have a good. Alright, for exercise, don't hate me, do it again, do A cross B.
Oh, you do B cross A.
The only way that you're gonna get this without having to look back to your notes is just do it over and over and over.
And you know what, I wasn't paying attention, I did A cross
You did A
B,
cross B.
and I got plus
Wait,
E.
wait, 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 wait. We'll see what we get.
It is good.
Alright, so what do we notice about A cross B versus B cross A? Yes. So what's really happening if this is just the negative of that vector? Like geometrically thinking, what's happening in space?
Yeah, because it's pointing in and just pointing out on the z-axis.
It's pointing in the opposite direction.
Yeah.
So don't forget, when we reviewed vectors, if we had vector v, we found negative v, just pointed in the opposite direction. So I gave you that first example with the two markers. If you find your third vector that's perpendicular, then just flipping the order is going to give you just the opposite direction. That's why that right-hand rule exists of which one to give you. The other one, if you had switched the order, just points in the opposite direction. So say, for instance, somehow we find ourselves where it wants B cross A, or it gave us B cross A, but I want A cross B. The goal is to not redo it. The goal is just to understand that, oh, if I just want to change the order, I can just scale that vector by -1. You don't have to rerun through it. All right, so in our properties list over here next to cross product, we want to say that V cross U is equal to the negative of U cross V. The next fun fact for us, if vectors u and v are scalar multiples of one another, which, remind me, what does that mean if two vectors are scalar multiples? I can say those two vectors are,
Those vectors are parallel.
parallel. So if two vectors are scalar multiples of one another, in other words, if two vectors are parallel to one another, then the cross product of those two vectors, well, let's think about it. I've got a vector, but now I've got the same exact vector, so that's my right-hand rule, but my index finger and my middle finger point in the same direction. I don't know where to point that. It turns out that the cross product of those two vectors equals 0. So I want an example. If I ask you to show that two vectors are parallel to one another, you can show me two things. You can say, oh, well, they are scalar multiples of one another. For whatever reason, we can't do it, we don't want to do it. You could also show that the cross product of those two vectors equals 0. Please ask questions so far. Right now, we need this skill in our toolbox to just whip it out, just so we can start using properties for calculus purposes. All right, so go ahead and open up Desmos 3D.